Hello and welcome to the Unit 12 podcast on Section 25.3. Today we're going to be talking about nuclear transmutation. I'm Mr. Sakaguchi,
And I'm still Mr. Lin.
and here we go. Um, Induced transmutation. Transmutation basically is converting an atom of one element into another one.
And it's possible to induce that or artificially transmute an element. And you can do this by slamming a nucleus into another nucleus at high velocities.
We achieve this using particle accelerators. The ones you see below is an example of a large particle accelerator that was just recently completed.
So what they do is they use basically a gigantic magnetic tube and they fire a nucleus through that, and it travels a really long distance, accelerating the entire way until it slams into another one. Some people are afraid of this big one that Mr. Sakaguchi was just pointing at. People thought that if you slam two nucleuses hard enough, you'd create a black hole and the whole planet would disappear, which I thought was kind of funny.
So this is one of the ways we induce transmutation. You don't always need elaborate setups like this. There are smaller setups throughout the world where you can also induce, to achieve different things, which we'll talk about. There are many transuranium elements. Basically, any element that has an atomic number of 93 or larger was basically produced through induced transmutation in a laboratory.
So these are artificial man-made elements, and because a side effect of them being artificial is that they all are radioactive.
And in the figure below, you see all of our transuranium elements. In terms of practice problems, if we're going to ask you to write out a transmutation reaction, this is kind of what it would look like. Let's say we had aluminum 27. Remember, the 27 refers to the mass number, and so we have two isotopes, and this is what we're starting with. This is what it's changing into, and neutron bombardment means that's what we're hitting it with. And so our reaction is written here below, and I'll let Mr. Lin take it over.
This type of practice problem is more about identifying the bits and pieces about what's hitting what and what's being produced. So you can see that you have aluminum 27 turning into sodium 24. So this is kind of like reactant, that's product, and then say it's occurring by neutron bombardment. So that means that the aluminum 27 is what we're starting with. It's getting slammed by a neutron and outshoots a sodium 24 radioisotope. And also as a side effect, an alpha particle, one alpha particle is released in the reaction, and that's shown here on the product side as well. So it's just a question of placement on whether or not it shows up on the left or the right-hand side of the arrow. You just have to read carefully the verbs that are affecting this, that are describing this reaction.
And also remember, with these nuclear reactions, the mass numbers have to be equal on both sides of the arrow, as well as the atomic numbers. So 27 plus 1 is equal to 28. 24 plus 4 is equal to 28. 13 plus 0 is 13, and 11 plus 2 is 13. So this helps us tell us how relative amounts of each of our players here in our reaction.
Be aware sometimes you might also have a description that requires a coefficient in front of one of these isotopes, and you just need to multiply one or two pieces accordingly to make it all fit.
Right. In terms of rates of decay, we can measure decay rates. It's measured in a term known as half-life. Half-life is basically exactly how it sounds: the time required for half of a radioisotope's nuclei to decay into different kinds of products.
Now, when we're talking about decaying, we're not saying that the matter disappears. It's transmuting. It's changing from one element type into another. None of the mass is being lost. Okay, so you should also notice that as half-life occurs, one substance will decrease while another substance will increase. The equation for figuring out the half-life of a substance is shown here, where you have your initial amount, your starting material, and then half times the amount of time that has elapsed, the number of half-lives that have occurred.
Right. And then we can also represent N as little t over big T, where T is elapsed time and T is how long a half-life is. Half-lives for each isotope has been measured already, and depending upon the isotope, we could figure out how many half-lives have occurred or how much of an initial amount of mass would remain after a certain number of half-lives have passed.
And the understanding and knowing these decay rates is useful in real world scenarios because we use them for several things, not just finding out ancient artifacts, but we also use it in medical science to figure out things like discovering cancer in a person and that sort of thing.
So here's an example of a half-life problem. So if gallium-68 has a half-life of 68.3 minutes, how much of a 10 milligram sample is left after 3 half-lives? So here we have our equation. So the initial amount is going to be 10 milligrams. The number of half-lives will be 3. The 68.3 minutes happens to be extraneous information in this case. And then we just go ahead and we plug in and solve. So 10 times 1/2 to the third gives us 1.25 milligrams left over.
Right.
I'll let you do 2.
And in this example problem here, we're going to start using the little t big T, and we'll use the information. So if the half-life of polonium-214 is 163.7 microseconds, how much of a 1 gram sample remains after 818 microseconds? So we have our initial amount given as 1.0 grams. Then we have our half, and then to the power of little t over big T. Little t is the amount of time that has elapsed, so that's 818 seconds. And then the half-life is our big T, so that's 163.7 seconds. And then you take, find the fraction of that, and then you take 1/2 to that power times 1, and then you get 0.03125 grams remaining after that amount of time.
Hold on. As Mr. Lin stated before, we can use half-lives to date certain objects. Basically, what we can do is we can look at the present state of a substance, and we can back calculate how many half-lives have passed to estimate the age of different types of samples.
So as you can see here, one thing to be aware of actually is that nuclear reactions are constant. They are regular. They do not change at all. And so because of that, we can figure out, like a clock, how old something is because of their half-lives. The diagram to the right shows you where radiocarbon 14, radioisotope carbon 14 comes from. And this is also entering your body at all times. As you can see in the diagram, we have cosmic radiation that's bombarding carbon dioxide in the upper atmosphere, and that bombards nitrogen, which turns into carbon 14, and then that carbon 14 winds up in the CO2 that plants will absorb, and the plants get eaten by certain primary consumers, so like a horse or a cow or something. We eat the cow, so on and so forth. Everybody gets carbon 14 in their system eventually, and that winds up getting buried, possibly fossilized, and that's how we have carbon 14 in a living substance. And then when we dig it out, we can measure how much carbon 14 is remaining inside of the specimen, as opposed to how much nitrogen 14 is remaining. And then from this ratio, we can figure out how old that fossilized sample was. And you can also do this with uranium as well. And they did this originally for rock samples.
Yeah, one thing to keep in mind with carbon dating is that as you consume and as you're alive, your carbon 14 ratio remains constant, and it doesn't begin to change till after you die. And that's where the conversion to nitrogen 14 occurs.
Right.
And I think that's it.